Well, I mean, that's pretty much what we'll be doing. We're going to continue on with our SAC preparation. So unless there's any topics in particular you guys wanted to focus on, we will continue on with where we left off. So, question 4. We have an electronics company designing a logo, and the logo is kind of like the Pringles mustache. It's given by those two functions, both circular functions. Yeah, that's just telling you that there's a shaded area, and we don't necessarily want to figure out what the total area is, more so write our equation for finding total area in terms of this so that we can solve for A. Alright, so we know that finding area under a curve or bound between curves has got to do with our integration, right? Which should make a lot of sense. We got this integral here. We've also got this domain of 0 to pi, which is a bit interesting because 0 to pi would be there, whereas the full thing we would normally imagine to be 0 to 2 pi. Furthermore, another weird bit, it's just sine. Now yes, these are both sine, one of them sine 2x, so it's a bit interesting to see how those might condense into each other. And there's also a coefficient here, which, yeah, they both have coefficients, makes maybe enough sense that we could be potentially taking one out. So our goal isn't just to create an area formula for this whole thing, but to create a very specific area formula that we can compare directly to this. I'll pause there while you guys have a think about what might have to be done. One hint could be to consider how circular functions have symmetry in them. Oh, you're going to say something, Nihal, I think? If you are, it's not coming through. Might need to check your audio settings.
Can you hear me?
Yeah, that worked.
I was going to say we can start off by doing we can start off by finding the area between two curves normally, then try and match up whatever we get to the thing that's given.
Yeah, okay, let's give that a shot. So, if we wanted to find the area bound between these two curves by the normal way, what are we going to do?
I've noticed something different.
Mm-hmm.
So the area should be the same as sine of like the area enclosed between the x-axis and the bigger sine curve, because the part that's like taken away is like flipped to the other side.
Are you talking about like this cutout here?
Yeah,
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 this cutout and this one here.
yeah.
Yeah,
They're basically the same area, so
yeah, they are exactly the
yeah,
same.
yeah,
That's a really good observation. You can also make that observation over here as well. This
yeah,
bump is the same as this bump. So in reality, you can consider no bump here and just filling that in. No bump here, just filling that in. And so with that in
yeah.
mind, that can help us get a bit further using a bit of symmetry stuff. Yeah, good idea.
Yeah. So I think the value of a should be 2 because the um, in integral of 2 sine x between a domain can be written as 2 times the integral of sine of x over that domain.
So domain is 0 to pi, worth
Yeah, 0
pointing
to
out.
pi.
So that would be just giving you this bump. We do want the full thing. So
Yeah.
To adjust for that, what we do?
I think we'll have to split that up.
Yeah, tell me how.
Um, okay. So first we write the whole thing. So integral of 2 sine x from 0 to 2 pi. We can take out the 2. Wait, no,
Now,
actually,
what I'll do is I'll pause here for it. This integral. Now, definite integrals by themselves give you signed area. This one is total area, so you want to make sure that anything that's positive is anything that's negative is considered positive. So the whole thing remains positive. If you were just to do 0 to 2 pi here, you would be considering the pi to 2 pi section as negative, and they would cancel each other out.
Yeah. So you'll have to split it up from 0 to pi and pi to 2 pi.
Yep.
Yeah, flip the pi to 2 pi.
Yeah, we can do that. Other way around, yeah. So, should be pi here, 2 pi there. Yep, that'll make them both positive.
Yeah. Okay, we can take out the 2 from both of them. Both of them are the same, like the inside part. So can we join them?
Yeah, these are identical here. Circular functions have equal positive parts to negative parts. So if we've already gone ahead and flipped that to being positive, then these terms are functionally identical. So it's the same as having yet another copy of this. This is 1 sine x, this is 2 sine x.
Okay, but what do we do about the negative part?
Well, you already sorted that out by flipping the terminals. So by flipping the terminals of what you're doing your integral as, you flip that from being a negative to a positive.
Yeah, but
are you like worried about you want it to be negative, or?
Oh yeah, okay, I think about it. Yeah.
Yeah. So, so from the beginning, you're like, okay, let's get our total area formula the way we normally would do it, with a little bit of symmetry to knock out the other function. We were able to fill in those holes, so to speak, which would in reality just make it integral of the first half plus the integral of the second half, so long as we flip the order of the terminals to make it go from a negative to a positive. Then from there you said, cool, we're adding them together so we can take out the coefficient of 2. That's nice. And lastly you said, these things are identical. One of these and one of these makes 2 of those. And all I did was make sure we took the one that actually matched up what was in the question itself, where we were using the pi to 0, or 0 to pi thing. So final coefficient, once all was being taken out, and we can directly compare, we're going to get a equals 4 for that one. Decently hard question. This was a VCAR one, 64% fail rate there. So more people didn't answer it or didn't answer it properly. In fact, a lot of people apparently wrote a equals 2. It's a very common mistake for that one. Because they just, I guess it's a very similar idea to what happened here, forgetting one portion or another of it. Any questions there? If not, let's move on. Okay, we're changing the circular functions. Cool. Draw H, yeah, whatever. I'll just get a sequence of graphs going on the CAS so we can compare them without even really thinking too hard. We can see the dilation factor is different and the period's going to be different. So the h of x should be a smaller graph and should be faster. For CAS, always use radian. Yeah, basically the default's always going to be radians. It should be fairly obvious for the most part, because they'll be using pi values for radians, and they'll be using the literal degree symbol for degrees. And so yeah, you'd only ever be using degrees if they ask for it like to the... in fact, if we have I think there was an older question here. Find angle to nearest degree. Like it tells you, put it in degrees to have your answer. Sometimes I'll use the degree symbol. They'll have like theta degrees rather than just theta. These are the things you would watch out for whether or not you're going to be using radians versus degrees. Okay, so we have 2 sine x, and then we had a third sine 3x. We're doing it from 0 to 2 pi. And so that'll be our graph. Now, to put this, like if you're actually answering this, you will do a very similar thing. You just want to find what your x-intercepts are via the CAS and what the peaks and troughs are. But that's sort of whatever. Or at least the x location of all those things. Is there a CAS function to go between degrees and radians? Yes and no. If you have the old one, you can't click this button, which would otherwise convert between radians and degrees. You guys should all be able to click that. That's an actual button to go between radians degrees. Otherwise, it's fairly trivial. You just, 180 and pi, any combination of the fraction, depending on which way you want to convert. But yeah, you guys get a bit luckier. You can click a button, and it's just there. Yeah, precisely. Okay, cool. So again, copying this sort of down, you already know the amplitude is a third, so the peaks and troughs y values are going to be plus minus a third. They're even written on our axes if you have a look back at the paper itself. Now, the interval ticks themselves I'd pay close attention to. So how many ticks there are is going to determine like what fraction of pi you have to work with, and they're going to line up with what we've got here. So what's this? We got 1, 2, 3, 4, 5, 6. So they're all pi over 6s. 0, pi over 6, 2, pi over 6, 3, 4, 5, and 6 pi over 6. So you'd likely see that all of these x coordinates are some pi over 6, which makes enough sense because 2 pi on 3 is the period of it, and then quartering that, yeah, makes enough sense. But yeah, as for finding them, you could probably just do your CAS solve for x-intercepts, your f-maxes and f-mins with appropriate domains, and that'll get you all the relevant stuff you need. The more challenging question here is going to be stating a sequence of transformations to get from f to h. So f is the big one, 2 sine x, h is the smaller one, third sine 3x. Now, this isn't as nasty as it could be, but we just got to make sure we're getting the terminology right. So, does anyone remember how we do determining a sequence of transformations? There's 2 methods we can do actually. So the 2 options you have are your x dash y dash, so you can use your point notation version of doing the transformations. The other approach is to do transformations by recognition. Transformations by recognition is faster. You're practically just doing algebra to get from one to the other. Now, the challenge in that is how you actually apply the algebra, because it's not quite algebra. What you're really doing is going from, like, saying, like, I don't know, if I do f of 2x becomes some new function ux, it's not algebraically consistent to be able to shove a term in the brackets. So it's more about substitution than actual algebra to do it that way. But let's explore it anyway. So when we're doing this sort of thing, we're typically trying to do it in order of TRD. And the reason why is because reflection and dilation being multiplication, anytime you have multiplication in your function sequence, any translations, any pluses or minuses that you've put in the function will be modified. So, like, let's say there was a +1 in that, and I wanted to make this dilate factor look like this dilate factor. Well, I'd have to try and divide this function by 6 to make that work. So I would have my 2 sine x plus 1, and I'd be applying a division of 6, but because it has to apply to the whole thing, I can't just put it on the front. That +1 now becomes +1 over 6, which we otherwise wouldn't want. Whereas if it was there, what we could do with our translates is start with a -1. Right? Putting a -1 would immediately cancel that out. Then when I go ahead and do my multiplication of 1 over 6, I'm just multiplying 0, so nothing ends up happening. So that's a bit of the rationale as to why you would do it in the TRD method, because when you do your translates first, you have those fixed. I've kind of just realized that I've said that in a little bit of a weird order. That only really works in this scenario. We'll revise this more properly. let's just do this one example first, and I'll go and be a bit more detailed on that, or a bit more nuanced rather. So the example that we had here didn't have any translates, so we can ignore this part. Nor does it have any reflections, so we can ignore that part. Dilates, I've already kind of shown you what to do, at least for the first bit, which is we want to convert this function to look like this function. We need to figure out what factor to multiply 2 by to get it to a third. The factor is 1 over 6. So x, and that's going to get us our 1 over 3 sine x. Then from there, well, maybe we should highlight that this is the factor we've used. Then from there, I need to figure out how to get these to work. Now, I've also just noticed, have I had a crash? Can you guys still hear me? I'm noticing my screen isn't moving. Am I back? Okay. Oh, my camera just decided to kill itself. Great. That's what it was. Okay, we'll bring that back in. But what I was getting at was, we see that we have x in the brackets of the first one, 3x in the brackets of the second one. You would need to introduce a multiplication of 3 to make that work. A multiplication of 3 directly attached to the x spot. Okay, is camera alive again? It's picking up. Yep, cool. So we'll go ahead and do exactly that. Again, making note of that's what we've done. Now, here's the challenging part, what we actually describe these as. So I just want to make sure we're all on the same page here. Are we all caught up? Have everyone got the windows back to where they need to be? Should have the dilate of a sixth and the multiplication of 3 that we just did. Are we all good? Yeah, okay, awesome. So now we just do, or write, the order in which we did our transformations. So multiplication of 1 over 6. It's in the y dilation spot. Now, depending on how you want to write this, you could say a dilate factor of 1 over 6 from x, which is typically what you'll see in the textbook, and if I take a sneak at the answers, is also the kind of language they'll use for their answers. But it is alternatively also good to, or okay to say along the y-axis, because at least that way you know it's whatever axis you're saying is the direction for that dilate factor. This one, however, is a bit sneakier. So if we remember from like how horizontal translations can be a bit weird, where subtraction goes right and plus goes left, a similar thing happens with multiplications, where multiplications on the x are actually inverted when you write what factor was used. So this is actually a dilate factor of a third from the y rather than 3. The reason for that will become a bit more obvious when we pull up the transformation doc. So from y. Let me pull that up now actually just to make that clear. It's been a while since we've done transformations. I even misspoke, so it'll be good to revise that again. Determine sequence, yes. I'll pull that one up, I'll pull this one up. Okay, so if we have a look at how dilations work from like the point form version, we're using your x dashes and y dashes, they're all done in the exact same way, which is first up identify the way the transformation works, which is you have x dash as the same, and in this case if we're applying a dilate along the y or from the x, it is a multiplication on the y variable. From there, there's this step that essentially flips the order of things. You rearrange to get x and y on their own, rather than x dash and y dash on their own. The reason why you want those on their own is because we're trying to substitute back into some function to actually apply the transformation. So we do that flip. Then, when we sub that in, at least in this case, we'll notice that the y is not currently on its own. We then got to flip it over, which is why that whatever's left over here as a multiplication is the factor, right? The dilate factor A has been applied, and if we look at where A has appeared, it's the multiplication. Nice and easy. Where this is different is when you do a dilate factor along the x, or from the y. You're still starting off with A multiplying x, but in this second step, because you need to get the x and the y back on their own, it flips. You now have x dash over a, so when you shove it back into your function, you get x over a. So the dilate factor needs to be represented as a fraction, a division of x. So if you currently have 3x, the way to rewrite that would be having x over 1 over 3, because that would then convert it back to 3x, at least in our example that we had. There's no further need to rearrange things, because the only reason we rearranged further was that y was no longer on its own. We didn't have an actual function in its proper form. Whereas here, it's already on its own. We don't care. So we just leave it as is. And we can see what that might look like here. A dilation factor of 2 shows up as x over 2. So all that's to say is why putting a 3 in there is actually a dilation factor of a third. Any questions there? Do we need to like have another revise of all the transformation stuff?
What document is that one? The one you're on right now?
This will be in the functions relations module, transformations, and yeah, the first of the lot. But yeah, this explains the point form version of how to do it. I I find it a very helpful way of going about things, even if it is longer. It explains a lot about why there's so much weirdness in how the transformations are expressed. Like, why does plus sometimes mean up and negative means down, whereas for horizontal, negative means right, positive means left. It's weird things like that that get explained by that. The other thing I want to do is actually correct myself here when I was giving advice on how to do transformations by recognition. You actually want to go in the reverse order from what I mentioned. What I mentioned regarding doing translations first was only going to apply in that specific example that I mentioned, where you're actually zeroing out any terms. If the thing you're trying to transform into does not have a 0 for its horizontal or vertical translation, just like I mentioned before, any further multiplications you put in there will impact that. Like, for instance, you got to get from +7 to +12 here. My example, I was trying to zero them out, so it made sense to just knock out the translation first. But when you have a non-zero translation, if I just go from 7 to 12 and then put a multiplication on it, it's going to change it. So I should correct what I mentioned there, which is you're better served, globally speaking, doing D then R then T. But okay. Next up, we've essentially got some generic versions of the functions we were using. So instead of having like 2 sine x, we now have m sine x. And instead of having a third sine 3x, we now have the same thing but with n's in there. M and n, m is constrained actually, n is not. But our domain is still from 0 to 2 pi here. These are some funky little questions. Finding the area enclosed by the graphs if n is even versus if n is odd. Where to go from here? Well, noticing the similarity of these functions as compared to the others is a good start, right? So one of them is just a dilate factor on the front, the other is a fraction and another dilate factor, where they're the same term. So if we look at the closest thing possible, we had this example here, which was we had 2 sine x and a third sine 3x. So if I plot the CAS, that's an example of what we'd have there. And if we look at the diagram in part A, we'll also see the example for n equals 2. So we can see what these are likely to end up looking like. As n increases, the circular function propagates more often. It oscillates more often, and it also has a much lower amplitude. So if we had a look at the n equals 2 example from the screen share, we'll see that it had a single cycle for the first main hump of the big one. Whereas if we compare to our CAS one, by having n equals 3, we ended up having sort of 3 little half cycles in there, a full cycle and then a half cycle afterwards. So we can kind of get an idea of what's likely to happen just by looking at what has already happened. So when it comes to finding our area enclosed, it's going to differ depending on whether it's even or odd, based on what kind of symmetries we can use. Let's try and explore that a bit more. So the good news is we can use sliders to help with this. I'm not going to quite do q of x exactly as written, just because I want to be able to see the graph properly. So we'll go, in fact even m kind of has nothing to do with it, so we'll just use regular old sine x, because nothing so far is toggling on m. So we'll just use sine x for the big one, and then we'll go, alright, well, we'll set this for second one, and we'll put the n only on the period bit, because we already know, or we should know well enough, what having a fraction of n would do. It would just essentially make the amplitude of it much smaller, and I want to know what's actually happening. Unless if I'd have n as that denominator, I'm not going to be able to see what's actually happening on the graph. But okay, so from here we can, well, maybe first set our window settings appropriately. 0 to pi. Let's go 1.5. That's not how that works. Go negative 1.5. Cool. Now, if we test all of our odds, let's see what we can observe. So n is 1, we can see they essentially are the same thing. You got one half cycle per bigger half cycle. For n is 3, we have 3 half cycles. For n is 5, we're probably going to have 5. 1, 2, 3, 4, 5. So we can see that effectively whatever our integer value our n is for odd, we're going to have an odd number of half cycles, an equivalent number of half cycles in the circular function, this half bit here. If we test all our evens, we're going to see a very similar thing. So we have two half cycles there. 1, 2, 3, 4 half cycles for n is 4, and probably 6. 1, 2, 3, 4, 5, 6 half cycles for that. Now, why do we care about doing this? It's because we're going to be able to observe what kind of symmetries we can use here. We use a symmetry in the beginning of this one when we had n is 2, where we said, okay, well, it's equal parts, the smaller circular function is equal parts on top and bottom, and so if we're cutting out a bit from the top and adding it on the bottom, the same amount on the bottom, we might as well just pretend it doesn't exist. Because we can effectively translate that to fill in the gap. So with that in mind, when we create our area enclosed graph for all n is even, we can ignore q of x and go back to basically doing what we were doing before, where we're just using our f of x, or whatever they've called it this time. And all we would be doing there, if we're doing total area, which we are, we're going to not need to have q of x at all. That would just be what could be written in terms of just that function. However, I have noticed it does want n in there, so maybe we shouldn't do that. That's a bit of a shame. I was hoping we were able to completely remove it, but I guess not. Okay, let's try a different way then. Area enclosed by the graphs. So just by quickly looking again at our functions, what's top and what's bottom becomes a bit of a challenge, because, well, I kind of am only looking at that one, aren't I? If I did have n in here, would that still be an issue? The answer appears to be no. So yeah, I would say what's top and what's bottom actually is quite consistent the whole way through. Especially if I use the m greater than or equal to 2. That's certain. So if we set like the absolute smallest possible value for it, it's well and truly above. So with that in mind, we're going to have k of x is always above q of x over the domain that's relevant there. Now, what are we going to do here to actually get our n in there? I guess we'll just see where it leads us, huh? So we're going to have area is going to be the integral from 0 to pi, or double it rather. So double the integral 0 to pi of top take bottom, where top is going to be k of x and bottom is going to be q of x. From there we would have to anti-diff and substitute, so let's do that. So let's go capital K of x, so sine anti-diffs to negative cos, so we're going to have negative m cos x, q, we had 1 over n sine nx, so that's going to be 1 over n squared, yeah, minus 1 over n squared cos x, yeah, they're both negative because we're going from sine to cos. You can obviously cas this out as well, you don't have to think as hard as I'm doing. And that also, it's also pretty good. We've seen where our n squared is likely to come from. So when we're doing our area formula, we're now going to have two lots of, let's maybe take a step back. Let's define some new function h of x as k minus q, because that'll get us the actual function we want to have as our full antidiff. So when we do our area formula, that's going to be 2 times h of top minus h of bottom, h of pi minus h0. That's going to be 2 bracket, so h of pi just means k pi, so that's minus m cos pi, h pi minus q, so it's going to be minus minus for the plus, 1 over n squared cos pi again. That's just doing h pi minus h0. It's going to be the exact same as this, but with zeros instead of pi there. Minus m cos 0 and plus 1 over n squared cos 0. You can see these get quite long. Let's continue. What we're going to do now is simplify what these are. So cos of pi, if we think of our unit circle, pi is here, which means the x coordinate is going to be -1 for that. So these cos of pi's are both -1, giving us m and -1 over n squared. We got this bit, cos of 0, 0 is over here, that's +1. So +1 times -m and +1 times 1 over n squared. Then from there, continue to simplify. M minus 1 over n squared plus m plus 1 over n squared. So this is what I was worried about happening, having them just delete each other. Is b just 0? Do I just go like this? Because it sounds like they should have deleted each other. 0 an integer, yeah. We saw already that the other function should cancel itself out. I think if I was doing this live in the actual exam, this is what I would leave it at. Let me see if I'm right in the answers. Oh, what a piss off. They actually did do that. They did want you to literally write 0 over n squared. So it should come as no shock that 12% of people got the marks for this one. In fact, I think that's rather high, all things considered. So, yeah, I guess it was good, safe. It was a safe idea to ignore the cancellation of those functions like we did before, to try and get the n squareds in there, even though we kind of knew ahead of time that they should be deleted. And the safety of it was that we now at least had some idea how we're going to put this n squared thing in there and make it work. That's a really awful solution, but it is the one. Because if you just go ahead and cancel it out ahead of time, you pretty much see nothing but just the 4m, because you would go from here and you would just say q of x6 is ignored, and we knew from before we just got to double up on this again to sort it out. Which is, you know, if you just anti-diff your k, yeah, it's just going to get right back to having the 4m. So yeah, that's a very weird one, but something worth considering, I guess. If they're saying to force it to a particular form, you can introduce a 0 in there to make it work. First time, I think, as far as exams go, that they've ever demonstrated that that's a valid idea. So keep that one in your back pocket, I guess. You would never feel good about leaving that there, though. Right? Like, that seems very odd. Are there any questions as to what I did there at all? I know it was rather complicated, but it basically just came down to doing the same thing we did at the beginning, which was find our area formula and go from there. This one, we didn't have to evaluate it. The example that we just did now, we did have to evaluate it. This previous one that we did had numbers, this one that we just did now had letters. That's really all that's actually different here. So hopefully that's made enough sense. Now if n is odd, nothing actually really changes because we did it from a position of ignoring any symmetries altogether. So I guess one of the advantages of doing it, the other advantage of doing it this way, is we don't have to create a separate rationale for our area formula. Like, if you remember from our exploration, we saw that for any odd n's, we had kind of like a half cycle to spare every single time. And so we could potentially use that in some way, but because we've done it in a way where it works for any two functions, because one's on top and one's on bottom always, we can actually just make use of the same things over and over again. Like in this case, if n is odd, what's going to actually change here? So n being odd, the functions are still going to be the same, so they anti-diff the same way. The area formula is going to be the same. Top take bottom. Let me just quickly validate the top and bottom definitely are still always consistent for odd as well as even. If we go n is 7. Yeah, top take bottom are definitely still consistent. That's good. Okay. So with that in mind, this is all still good. The anti-diffs are therefore still good. And is doubling up on the area still appropriate? So if you do top take bottom on this, get all of that. Yeah, they should, whoops. Bugger. Actually, n equals 5 is fine as well. Okay, so let's see. We've got 1, 2, 3 above, 1, 2, 3 below. Yep, these should be identical, so we should be able to just double up. That's still fine. Okay, so we're allowed to double that up. We're still going to be shoving in pi's and zeros. Oh, it's sine nx. I did my... whoops. I did this wrong. Okay. Did that matter? That did matter, actually. So we kind of actually got lucky. Uh-oh. I did my anti-diff wrong. Hang on. It's any q. That should have an n in it there. That should have an n in it there. Yeah, okay. Let's revisit that then. So from here, cos n pi, if we're assuming it has to be even, then any even value of pi, all the odds are over here, all the evens are over here. So this is your 2 pi, your 4 pi, so on and so forth. So this ends up being positive 1. Similar thing over... oh no, that's just still 0. Positive. Oh, I even screwed up the algebra as well. This is positive and that should have been negative. God, I made a couple of mistakes that cancelled each other out there. I got really lucky with that one. Good God. Come on guys, you gotta call me out. Anyway, we'll fix it up proper for the next one. So, for the next one, all this, as we discussed, is going to be more or less the same up until this point. So let's write out that. A equals 2, bracket. So it's negative m cos, yeah, that's still going to be the same. Negative m cos pi. 1 over n squared cos n pi. Minus the 2 minus m cos 0 plus 1 over n squared cos n 0. Okay, now we actually have what we needed. My phone's bugging out. Oh god, it's slow. It's gonna crash again?
Is it just me? Is it lagging out a bit right now?
I think it's lagging. Can you hear me good enough, or is the phone...
Yeah, you're fine. I think it's just the camera.
Yeah, I think it... has it come back now?
Yeah, it's back.
Yeah, looks like it. Cool. So right and right. Yep, okay, we're back. Cool. A equals 2. So cos pi, still just negative 1, so that's going to be positive m. Now for this one, we're going to have a 1 over n squared. It definitely was positive, yes. Now cos n pi, this case we have n as odd. So if n is odd, again that's going to be all the left hand side values. Pi, 3 pi, 5 pi. So that's going to get us the negative 1. So, in other words, just replacing that with a minus. Then from there we're going to distribute our brackets properly this time. It's going to be plus m, because cos 0 is positive 1. This is now going to be minus, because that does come through. cos n 0, so if it's n times 0, n is irrelevant, it's still just cos 0. So that gets left as is. Cool. From here, m and m make 2m, minus and minus make minus 2 of that thing. And so finally, to get it in the right form, it's am, yeah, same form exactly. It's going to have 4m minus 4 over n squared. Let me check that one. Yeah. Oh, actually I did make a final answer mistake. Check the format of the question that it wants me to get my answer in. This is a correct algebraic answer, by the way. I didn't screw up again. But check the format of what's supposed to be given versus what I gave. A equals 4m minus 4 on n squared. I went wrong a little bit here.
Is it the positive?
Yeah, I got to write as a positive, as a plus sign there. So if I was to rewrite this, what I should have done is that. And that most closely matches the format, because b is allowed to be any integer. Integers can be negative. Even though it's not normal to write it like that, it's the form we were given. Same as it's not normal to shove a 0 in there, even though we can. Because yeah, I remember doing this and I was like, I could have sworn there was something to do with odds and evens in the actual circular function evaluation. So I got incredibly lucky to still get the right answer without even having the n's in there. That was 2 compounded mistakes on each other. One with not including the n at all, and the other was not distributing properly. But hey, I guess we've all been there at some point, right? Anyway, so that was an exploration in the differences in odds and evens, and using the circular function symmetries yet again, but this time more so in terms of unit circle rather than in terms of graphically observing the cancellation of area and such. Any questions to wrap that one up? If not, we'll move on to some of this, which, let me have a look actually. We're doing maxes, intersection points, tangency. Yeah, okay, so they all do. You'll find is a very consistent thread whenever they do these exam style questions of calculus. It'll be a bit of diff at the start, and then it'll lead into some sort of area thing later on. The one that we just did was pretty much predominantly area related. It's more common to get something like question 5 here, where it does a bit of functions, a bit of diff, and then into your bound area from there. Okay, these should be a nice refresher with some simple starting questions. Finding the x-intercepts of a function. I don't even think we need to talk about it at all. X-intercepts are always solved by y equals 0. So let's do that. I'm going to clear the workspace, make a fresh one. It's probably important to use the actual letters they've used so we don't get confused on which function is which. Negative x cubed plus a times x. Do not do just ax, otherwise the CAS will think ax is the variable, whereas you want a and x to be separate variables. And then yeah, a31 function equals 0. Jeez. X equals a or x equals 0, which you also probably could have solved by a quick factorization, but it's good to have it in the CAS anyway. Local maxima for f, there's about 1 billion ways you could do this. How might we get the maxima of f?
Find the derivative.
Yeah, diff equals 0, perfectly fine. ddx fx equals 0, comma x. That's going to get us those. Pretty likely that one's the max and one's the min. This is a cubic after all. How do we know? A couple ways you could find out.
And I didn't understand. Can you repeat that?
Oh, so we got two options there. One is likely to be the max, one is likely to be the min. How would we know?
We look at the behavior of the graph. So this one's going to be as x goes to infinity, y goes to negative infinity.
Yeah.
So the behaviors flip, and the first turning point will be a minimum. The second one will be maximum.
As in from left to right, it'd be something like this. Oh, well, it's loading. Is my phone going to crash again? I guess we'll find out. There it goes. Draw, draw, draw. Negative cubic is what you meant, yeah?
Yeah.
Yeah, that's fine. So,
Chris.
yeah.
Quickly. Your camera it's back now. I just wondering, can I just see what you put into the CAS again quickly?
Yeah. Looks like it's back up online again. So this is just solving derivative 0 to get stationary points.
Okay.
Yeah, I've done it all in one line. So defining f
Yep.
and then yeah, that's one way of doing it. Being able to identify the function itself by looking at the extremities or just seeing that it's a negative cubic. Other approaches could be substitution of those values and see which one comes out to be a bigger value. Other approaches could involve f max, f min. So if you do f max, for instance, challenge with that is that you get the global max, not the local max. So that probably doesn't even work actually. Yeah, if I just do this, it'll get me, because there's no like domain restriction, so it will just shoot negative infinity there. So yeah, diff was actually probably the only way, besides graphing, to go about that. Cool. So with that in mind, if we have those two as our option, and a has to be a positive real constant, then that means that 0 would be the x coordinate that we would want to use, because it's the leftmost rather than the rightmost one there. Oh, sorry, hang on. We're looking at the local maximum. Right. So it's the other way around. One of the rightmost one, because the rightmost one was the max. I thought we were doing min. Next up, values of a for which... Okay, that's going to be a unique kind of question. Since we're about to hit time... Yeah, I'll just sort of briefly talk about this one. So, find the values of a for which the graphs of f and g have just one point of intersection. First thing you might want to do would be figure out where do they have points of intersection. So I'm just going to quickly define g of x. Pretty sure it was just a linear. Yeah, it's just ax. First thing I'd want to do, figure out where they intersect and what that looks like. They're going to intersect at plus minus square root and possibly also x equals 0. So that's 3 possible options there. We want only one. My favorite way of doing this is to just say, okay, I've currently got 3. I either want to make all these solutions become the same, so they should all say x equals 0. Whatever value of a I choose should force this to be 0. Or I do it in such a way where the solutions become undefined entirely. The fact that it says find the values of a is going to inform that I want to do the last option there, which is find a way to make these undefined, because when it comes to square roots, you can make them undefined for a lot of different values of a. square roots become undefined so long as the brackets, the thing inside the root is negative. So all I'm going to do is rip out exactly what's in that root and see where it goes negative. A times bracket a take 4. Where does that go less than 0? This is going to be our set of values for a. So we would be doing a between 0 and 4, non-inclusive, because that makes these two solutions undefined, leaving only one possible solution, x equals 0. I'm happy to stick around and explain that in a bit more detail should you wish, but if that was sufficient and there's no further questions, that'll be it. I'll leave you to enjoy the rest of your day. No worries. Thank you.
I've got a question.
Yep.
So about the videos you post on YouTube, like how do you name them? Because I'm a bit confused on like finding which video I need to like rewatch.
Yeah. So that's the challenge with going based off of the YouTube, which is I try to get it as consistent with what's in there as possible. Like all the SAC revision stuff is kind of just part 1, part 2, part 3. It's probably better to look rather than through the YouTube stuff and go through instead the past recordings stuff, because that's at least you can see what week each thing was relevant to. That's probably the best way of going about it,
I see.
because you'll see pretty quickly where it starts, and you'll know if there's a particular question you were looking to do. If that paper is clearly visible on the thing, you'll see it quite quickly. Was there a particular thing you wanted me to try and find out for you?
No, it's fine.
Oh, okay. But yeah, probably the best way to go about that would be in the actual past recordings module, because you can see which one was for which day, and the title is more or less the best I can do with it. Like any of the Friday classes are called Math Methods Review, at least recently. And it just has, like last time it was Integration and Calculus SAC. Last time before that was Logarithms and Calculus, because we had I think it was a student submitted question for logarithm stuff.
Okay.
That's sort of what I'm thinking through when I'm putting the titles together.
Alright. Okay.
Cool.
Yeah. Thanks.
Yeah, no worries. Thanks for coming.
Have a good weekend.
You too. How you doing, Taihan?
Yeah, good, thanks. Oh, I was just wondering, were you explaining more or were you done for tonight?
Oh, this would be it, unless you had anything you wanted me to explain further.
Oh, okay, no, that's all good then.
That's all good.
Just wondering, like, what advice would you have for integration? Like, what I should be doing?
Probably this sort of stuff. Is there any concepts of integration that you still need to like properly learn from the ground up?
Not really, but it's probably like the areas, like just like in general, the least confident with, to be honest.
Yeah, maybe do the chapter review on the integration chapter as a whole, and just see how you go with that. Start with your short answer, go into multis, and then extended response. See if you're falling short in any of those. But if you're just doing things here or there where it's like, okay, I see where I got that wrong, then it's fine to just keep grinding through them all. You know, a good benchmark to have, depending on the length of how big the chapter review is to see, can I at some point in my studies do the whole chapter review end to end without making a single mistake? Because you have unlimited shots on goal there. The questions aren't changing. So
Yeah.
as long as you're doing it at some point where you can do the whole thing end to end without any issues.
How like accurate is it compared to like the final exam?
I mean, I like them. So you can already see, like, a lot of these were pulled from VCAR. I'll just for now, I'll pull up the textbook and we can do a little comparison and see if they look the same, more or less. So we've obviously been focusing on the extended response sections, so let's go ahead and do that.
Yeah, just because it helps to know like whether or not it matches up.
Like, for the vast majority of them, I like them a lot. first. Let's see if this is going to be any different. Yeah, a bit of diff stuff and then goes to area enclosed. That's literally what we're about to do here. Maxima,
Yeah.
bit of diff stuff, cool. More area, more area.
Yeah. Would
Yeah.
you think? Yeah. Would you think of just going through this for the integration SAC? I guess.
Yeah,
'Cause I'm assuming it's gonna like include like obviously trig and a little bit of diff probably.
yeah, yeah. It'll be a bit of function stuff, so you can do things as basic as finding x-intercepts and intersection points. It's not going to go too... Oh, and circular functions is a big one for this sort of thing, because it does tie in so nicely to area, because you can do
Yeah.
a lot of the cancellations of areas.
Yeah. The main thing that annoys me is when like they just use like a trig equation for like absolutely everything.
Well, get used to that, because even in probability, they'll chuck trig at you for some... for some
Yeah, it's like they never
probability
use like
models.
just like a regular equation. It's always like sine, cos, tan, this or that.
Yeah. No, 100%. But yeah, like these will be good. It looks like even some applications which we don't seem to get too much of that in the VCAR exam. The applications of integration, like when you have to anti-diff your rates or change stuff.
Yeah, that was probably the hardest chapter.
Yeah, it's the hardest to think about like what you're actually getting, and fundamentally, as long as the thing that worked for me in that was understanding that definite integral is area under curve, but definite integral is also just antidiff and then a subtraction. And if you think about doing a subtraction, you just find the difference between where you started and where you ended up.
Yeah.
And so if I'm anti-diffing a rate equation, the function that I'm doing a subtraction on is the quantity itself. So if this is a, what is this, velocity? Yeah. If this is a rate of velocity, well, I guess it's just velocity, not a rate. If I anti-diff velocity, I should get up to position.
Yeah.
And so by doing a subtraction on positions, I'm literally finding how far did I travel from position 1 to position 2.
Yeah. Yeah.
So thinking
that
about it
makes
in
sense.
terms of those two steps would be...
Yeah, I mean, because for us, like the whole thing, because this SAC was like the whole thing was just extended response, and it was just like a huge like complicated scenario, and then you had to like figure out like how to turn the slab of English into math.
yeah, precisely. Was it similar to that practice sack that I had? Oh, that you gave me?
Not really.
Not
to be honest.
really.
It was like I'd have to draw a diagram. I don't know if I can really explain it.
Yeah, that's fair. I mean, if you get the paper at some point, feel free to send that through so I can add more context on it. But yeah, if it's anything, because I found
Yeah, it
this
was not. It
also...
was nothing. It was nothing. It was like the whole diagrams, and you had to like, It was pretty a little bit related to function relations, I guess. Like you had to like figure out like your own kind of stuff. Like I felt like this SAC was easier, or maybe that's just because I understood it.
Did you get to these ones as well, like the question 7 and beyond?
Oh, like myself.
Yeah.
Yeah, you used a bit of AI to help me.
Oh, sure. Yeah, okay. That's fair. Because yeah, those I mean, there's pictures, but I guess yeah, you're right. There's not.
But yeah,
too
the first
much.
couple that we went through together made sense. It was just like it just feels complicated when you see the question.
Oh, for sure. And probably the most complicated part of that might have been the subscript, like CN.
Yeah, that was
not
tricky.
noticing that is the same N as this.
Yeah.
Like for me, it's like I've seen so much of this stuff that's just second nature, but like that's very unique to methods. That this probably hasn't ever come up before in methods. So
Yeah.
understanding that, I made sure to put a bit more emphasis on what that actually meant.
Yeah.
But yeah, no, when you get that through, I'll be curious to see what that was all about, and
Yeah.
maybe I could put some pointers, because if that might still be similar to what you might get for the actual calc one, for the anti-diff one. I guess we'll see. But yeah, as far as what you should do, probably a good point of call would be to start with this. Maybe not go straight to the extended response. Maybe get some of the short answers down.
Yeah, like build up from there.
Yeah. and the multis as well, maybe just have like quick fire, like rapid. Okay, can I do this sort of thing or not?
Yeah, I think that's a good idea.
Sweet. And then after that, all my calculus SACs we've been going through already, so that's, you know, you'll at least have seen those for the second time when you do them for yourself. But there's 3 of them
Yeah.
in total for tech active.
Okay.
And so yeah, yes, we are using them now, but by the time you look at them again, you're probably gonna forget a lot of it
Because
anyway.
I'm pretty sure after this integration is just straight into prob, right?
Yeah, just prob.
And then after prob's done, that's done for the year, right?
Yeah, well, into the exams.
And as in terms of like content.
Yeah, exactly. And probs, I don't think it's that long. If we have a look at the chapter sections,
I've heard it's like more difficult. And that's just what I've heard.
yeah, what's the most difficult part? The most difficult part is probably understanding how they all interweave and knowing when to use what. And that was actually the reason, like the first bound reference I did of those lot was the probability one. And the reason I did it was mainly for that top half of it. I don't know if you read it too much, but it goes into detail as to say, okay, here's when you use this kind of probability versus this kind of probability. And that's pretty much all the focus is on the top part of that bound reference. It's basically its own lecture.
Yeah, like because for prob it's just like it. Does it like come together with like the calc stuff? Like
Yeah, so continuous is, just to give you like a brief heads up, there's this section called continuous probability, and basically what you're doing is you're treating area under curve as probability.
oh yeah, I can see limits.
Yeah. So like any function that you use for probability has to have a total area of 1, and then any area subset of that is considered the probability of going from left to right.
Oh, that's actually an interesting way to think about it. Probability in terms of area.
Yeah, it's used for continuous quantities where it doesn't make sense to say like x equals 1, x equals 2, x equals 3. You want to have a continuous infinitely precise domain.
Yeah.
But that's a snapshot for later.
Yeah. I'll send many messages on the school if I have any questions about the integration.
Yeah, sick. Send them through. Even before the lessons as well. If you want me to go through anything specific, we can focus on that.
Yeah. Sure. Sounds good.
Easy.
Thank you, Chris.
I'll leave you to it. Have a good night.